All right, today we are diving into something pretty huge from Google DeepMind called Unified Latents. It's a new framework that takes on one of the biggest headaches in generative AI, that constant battle between making incredibly realistic images and the insane amount of computing power it usually takes. And well, they might have just cracked the code.
So here's the plan. First, we'll get into the fundamental trade-off that's been holding AI back. Then we'll see how Unified Latents totally flips the script. We'll dive into the clever way it works, check out the absolutely state-of-the-art results it's getting, and finally, we'll talk about why this is such a big deal for the future of AI. Okay, so let's start with this big trade-off. In the world of generative AI, there's always been this constant tug of war, a core dilemma that forces developers to make a really tough choice. It's a challenge that has, for a long time, defined the limits of what's possible. Well, until now. I mean, at its heart, the question is pretty simple, right? Can we generate better, higher quality AI images and video, but do it using way less computational power? For the longest time, it really seemed like you could have one or the other, but no way you could have both. To get this, we've got to talk about latent diffusion models, or LDMs. The best way to think about them is like a JPEG file. You know how a JPEG takes a massive, beautiful photo and squishes it down into a smaller, much more manageable file? LDMs do pretty much the same thing for AI. They take all this complex data and shrink it into a simplified little blueprint called a latent space. The AI then builds new stuff from that compact blueprint, which is just way more efficient. And this is exactly where we hit the trade-off. If you make that compressed, latent data super simple, with low information density, it's a piece of cake for the AI model to learn from it and create new things. The problem? You lose so much detail, so the final image or video quality takes a big hit. On the flip side, if you pack in a ton of detail, high information density, yeah, you can get almost perfect quality, but that latent blueprint becomes so complex that it's an absolute nightmare for the AI to model. It's just incredibly expensive. It's this constant, frustrating balancing act. And this, right here, is where Google DeepMind's Unified Latents framework walks onto the stage, offering a really elegant solution to this exact problem. So what is it exactly? Okay, think of it like a symphony orchestra. Instead of having the violin section practice over here, the brass section over there, and just hoping they all sound good together on stage, Unified Latents trains them all at once as one single cohesive group. This joint training makes sure every single part, the compression, the modeling, the decoding, is all perfectly in sync, which lets them completely sidestep that old trade-off. So how does this framework actually pull it off? The real magic, is in its architecture and the way it's trained. The architecture is built on three really clever pillars. First, there's fixed noise encoding. It strategically adds a very precise, predictable amount of static, or noise, to the data. This basically acts like a strict file size limit, giving the model a clear target for how much to compress. Second, you have prior alignment. This just makes sure all the different parts of the model agree on that noise level, so they're all playing from the same sheet music. And third, a reweighted decoder. This part is like a smart art restorer. It knows exactly which details are most important to focus on when it's rebuilding the final image from that compressed blueprint. The training process is also just brilliantly designed. It's done in 2 stages. In stage 1, everything is trained together. The encoder, the prior, the decoder, their one and only job is to learn the most efficient latent space possible. Then in stage 2, they freeze that super efficient encoder and decoder, and they bring in the big guns. A new, much larger base model that is laser-focused on one thing, generating the absolute highest quality output from those perfect latents. It's a strategy of optimizing for efficiency first, then scaling up for pure quality. So the theory is super elegant, but does it actually work? Let's get to the fun part, the results, and see how all this cleverness leads to some truly state-of-the-art performance. And wow, the results really do speak for themselves. For image quality, they use a metric called FID, where lower scores are better, and it scores a remarkable 1.4. For video quality, measured by FVD, it hits an even more impressive 1.3. And for just pure reconstruction fidelity, how perfectly it can rebuild an image from its compressed form, it gets a high score of 30.1. I mean, these numbers aren't just good, they are pushing the very edge of what we thought was possible. Let's just zoom in on that video score for a second. 1.3 FVD. On the Kinetics 600 benchmark, which is basically the gold standard for video generation, that number is a new world record. It makes this framework, officially, the state-of-the-art for generating video, period. And that 1.4 FID score for images, that's where the efficiency part really shines. Sure, other models can hit that number, but they often need way more computational firepower to get there. Unified Latents delivers that same elite quality while using less horsepower. It's totally busting the myth that you need astronomical resources to get top performance.
Okay, so we've seen how it works and we've seen how well it performs. Now let's wrap it all up by talking about why this is such a huge step forward for the entire field of generative AI.
So let's just recap the breakthroughs here. We've got an integrated framework that optimizes the entire pipeline from start to finish. We have a fixed noise method that gives developers precise, predictable control. There's a two-stage training strategy that perfectly balances efficiency and quality. And all of this leads to state-of-the-art performance that is just fundamentally more compute efficient.
This quote from the paper really says it all. Efficiency. In a world where training AI models costs millions and uses up vast amounts of energy, a framework that delivers top-tier quality for less compute isn't just an improvement, it's an absolute game changer. And this all leaves us with a really provocative question. Now that the old compromise between quality and cost is basically broken, what comes next? With state-of-the-art AI generation becoming this much more accessible, what new tools, what new creative frontiers are about to open up for everyone? This framework isn't just a technical paper. It feels more like a key unlocking a more efficient and democratic future for AI. Thanks for tuning in.